So we're back from the break. Up to this point, we discussed, actually, let's make a recap of what we have already discussed, and then we can continue with the next points of this lecture. The first thing we discussed is that quantum chemistry is important, and there are many applications that quantum chemistry can help us understand, and many industrial processes that quantum chemistry plays a critical role on. At the same time, quantum chemistry in the real-time quantum computers and in the way that we currently tackle the different problems is based and relies on hybrid quantum classical algorithms, with variational quantum eigensolver being the most known one. We discussed the different challenges that one needs to take into account in order to make an efficient calculation using the variational quantum eigensolver and hybrid quantum classical schemes in general. And we also discussed how can certain approximations on the definition of the problem and the description of all the relevant pieces of the problem can play a good role in order to make the simulation fitted in the available near-term quantum computers. What we haven't discussed yet and can play a really big and important role is the way that we can make the solutions better and more accurate for the future systems. Computing the ground state for small molecules, as I showed you already, the results were noisy, so we were not exactly on top of the exact curve. And the question is, can we make the solution better? And the answer to this is yes, we can make the solution better. You see the results from 2017 on the left and the same results and for the same molecule on the 2019. And you see that now the white solid circles are much closer to the exact solution in comparison to the ones from 2017. There were many things that were applied in order to make it better in the 2019 paper, but mainly the error mitigation technique, that here is zero noise extrapolation, played a really important role that allowed us to get much more accurate results. Other methods that can make the solution better rely either in the development of the hardware side. In general, there is a discussion about the roadmap to the fault tolerance and how can we make better hardware that is going to allow us to also have significantly better algorithms for the solution. Then we can think from the algorithmic side and the application development side of reducing the different overheads, applying error mitigation techniques that I'm going to discuss right now, and start developing new algorithms that are significantly more robust. You heard about the different challenges that the variational quantum eigensolver has, and all these are good examples of how can we make the algorithms better and start thinking of what can we do in order to make the calculations more accurate and more exact in order to be considered valid for chemical simulations. Then another very important aspect is the software side. Software side will also allow us to experiment with more elaborate schemes, will allow us to think of what we can develop in terms of algorithms and what can we do in order to make it better. And these are things that one can consider as a whole picture that will allow us to get better results and significantly enhance the simulation of molecular systems and quantum chemistry in near-term quantum computers. A little bit about error mitigation. I'm sure you will hear more in the lectures around hardware about error mitigation, but the different techniques that one can apply in order to get much more exact solutions in quantum chemistry. The first one is the readout error mitigation technique, where we're using the post-processing of the different counts that are collected when we're measuring different observables, and we're using a so-called calibration matrix in order to map them back to better distributions and get significantly better results in terms of amplitudes and probabilities. With this technique, we can mitigate for the readout error, but the generation of the calibration matrix has an exponential cost that can also be mitigated if one use readout error mitigation that is not correlated between the different qubits. Another important readout error mitigation technique, which is actually the one that was used to the result that I showed you exactly before, is so-called zero noise extrapolation. For the case of the zero noise extrapolation, what we do is that we stretch the different pulses of the hardware in order to produce more noise. With these stress factors, we can think of going to more noisy calculations. And when we have different stress factors, we can extrapolate back to the case that there would be no noise. That is also the name of zero noise extrapolation, and that indicates that one can measure observables and get the energy with very good and accurate results of the energy and the different observables by using this technique. This is a more hardware level technique with some algorithmic components about the pulse elongations, but this is quite important, and this gave very good results in the recent literature. Furthermore, there are also algorithmic error mitigation techniques. Here I show you on the left the Lanczos error mitigation work that we recently published, where we actually try to enhance the ground state distribution and make it a little more accurate. On the right side, you see the use of repetition codes also as an algorithmic error mitigation technique, where we're using multiple qubits to encode one physical qubit. And here's the simulation of the hydrogen molecule on the right. Okay, so with this, I think I established the fact that error mitigation can really give us better results. And you can go from the picture on the left to the picture on the right. And now what I'm going to talk is that now we have some ideas of how can we get more accurate results, how can we go beyond what we have in the classical calculations, and what can we do in order to make it more accurate. And now what do we do when we have access to the ground state? How can we extend the variational quantum eigensolver in order to be able to simulate more interesting properties and start thinking about excited states, and how can we use excited states as a method to, so how can we measure excited states? So we propose the quantum equation of motion approach as a method to calculate excited state energies. The quantum equation of motion approach was proposed in the paper from Olitro in 2020, where we started by using the optimized variational parameters that came from the variational quantum eigensolver to create the equation of motion operators. And then eventually, by solving a pseudo eigenvalue problem, we are able to get the energy differences between the ground state and the different excited states. In this way, we can calculate the excited states of different molecules, for example, the lithium hydride that you see here. And we can apply, again, error mitigation techniques in order to get good and accurate results. You see here that we are able to capture the first 4 excited states, the energy of the first 4 excited states in a 4-qubit experiment that we did in the IBM Quantum Poughkeepsie hardware that currently is retired. Okay, so now you have a feeling of how can we go from the ground state to the excited states, and how can we leverage the different algorithmic components in order to be able to simulate more and more properties of the system. And now the question comes of software, and what can we do in order to be able to benchmark these processes, and how can we use these hybrid quantum classical algorithms, and how can we test and implement all of these routines. As I mentioned already, we have the Qiskit Nature module. It's a part of the Qiskit software where we can actually use and we can actually implement all these algorithms and test them and start developing more and more elaborate schemes. In the past, Qiskit was taking care of the full implementation, and now with the Qiskit Runtime, we're able to get significantly bigger speed up in order to do this kind of calculations. For the hybrid quantum classical schemes, the Qiskit takes care of the full implementation and the full integration of the two in the Qiskit Terra level, where we have all the algorithmic components. In 2021, we introduced the different Qiskit application modules, where we introduced the Qiskit Nature, Qiskit Optimization, Qiskit Finance, and Qiskit Machine Learning modules, which are used as a way to have more focused application modules, and the people that are interested in one of the specific domains can start using the different tools that are available for each of these domains. For the case of Qiskit Nature, we were able to go and start developing all the process of getting the one and the two body integrals, creating the fermionic Hamiltonian, do all the relevant mappings down to the qubit Hamiltonian. And the moment you have your qubit operator, then you can just pass it to the main Qiskit that will allow you to use the different algorithmic components that you have already heard about, for example, the variational quantum eigensolver or the quantum phase estimation or different algorithms about time evolution that you're going to hear later on. What we did when we rearranged the different framework is that we took what we used to have in the Qiskit Aqua and we moved all the parts that are related to algorithms and different algorithmic components into the main Qiskit, so-called Qiskit Terra, and all the application-specific components were moved to the different repositories which were specific for each of the domains. So Qiskit Nature, Qiskit Optimization, Qiskit Finance, and Qiskit Machine Learning. Qiskit Nature aims in bridging the gap between natural sciences and quantum simulation. What we want to achieve with Qiskit Nature is mainly the fact that somebody that is interested in simulating electronic structure problems or quantum chemistry does not have to bother about doing things like full quantum information and quantum computing related points. All these things are being automatically handled by Qiskit, and one can focus more on the chemical side. On the other side, someone that's more on algorithmic development person wants to test the chemical system, then Qiskit Nature can automatically generate a chemical system for you and give you the qubit Hamiltonian that you want to use for your algorithmic development. Then, in this way, Qiskit Nature allows researchers to model problems originated from natural sciences using a quantum computer without the direct need of knowing how to use all the classical quantum chemistry tools or all the quantum computing tools. We designed the full Qiskit Nature package with modularity and accessibility in mind without losing the applicability to real-world applications. So we want to be able to think of how can we scale it up, what can we do next, and how can we go to the next level of applications, especially for electronic structure and molecular systems. The general flow that we are following in the Qiskit Nature side is that we start with the generation of electronic structure problem. An electronic structure problem has an input, an important component, which is the molecule. The molecule describes the atomic composition of your molecular system, the geometry, and the different coordinates of the different atoms that you have in your system. Then you have your electronic structure driver, which is a classical code. Currently in Qiskit Nature, we are supporting PySCF, Psi4, PyQuanti, and Gaussian as electronic structure drivers, and we are thinking that classical codes are as a way of generating the one of solving the Hartree-Fock equation and generating the one and two body integrals that are needed for describing the system of interest. When you have your classical code providing you the one and the two body integrals that you need, then you go to a group property that stores all this information and can also calculate other quantities that are needed. For example, dipole integrals or Pauli operators or actually a group property can also generate the Pauli operators that are needed to measure different quantities. All these go through transformers, which can go and, for example, freeze orbitals that are close to the core, or carve an active space, or move to different symmetries within the system. And these transformers are operating as a classical pre-processing step before the generation of the fermionic operator and the fermionic Hamiltonian. The fermionic Hamiltonian needs to go through a ground state eigensolver that takes care of the conversion to the qubit operator, and the qubit operator then goes to a minimum eigensolver that is an algorithm that lives in Qiskit Terra and can eventually give you an electronic structure problem result. The electronic structure problem result is interpreted in order to be able to get all the information related to your problem and can give you all the quantities that you wanted to measure from the start. It is important to say that all this flow is really automated and can be handled automatically via Qiskit nature, where what you need is that you need to start by specifying a molecule, the driver you want to use, a transformer, and then this will eventually lead to an electronic structure result. So I would like to show you the tutorials that we have and how can one do the simulation of a molecule directly using Qiskit nature. Okay, so here we are in the GitHub page of Qiskit nature, and if one goes in the docs directory and tutorials, you can find different tutorials about how can you simulate electronic structure and vibrational structure, protein folding, lattice models, and many things that are available in Qiskit nature. Here we are interested mainly on the electronic structure problem, where we start from the definition of the molecular Hamiltonian and the calculation of the ground state. So we start with the initial Hartree-Fock initial state, which is a good approximation for the solution of the problem, and this is what we need to solve in order to get the one and the two body integrals. For this, as I mentioned, we are using classical codes that one can call directly from the Qiskit nature side, and this is an example that how one can do it in the software here. You see that we start from the definition of a molecule. For this particular case is the hydrogen molecule in an equilibrium distance. You specify the charge and the multiplicity of the system, and you need to specify a classical driver as the solution of the problem you are interested in. In this case, we're using the PySCF classical driver in order to generate the one and the two body integrals. Then what we are doing is that we are doing the mapping from the fermionic space to the qubit space. This is something that we already discussed. And for this particular case, what we are using is the parity and the Jordan-Wigner mapper. Starting, we generate the fermionic Hamiltonian by defining the electronic structure problem and the second quantized operator. And you see here that this is the fermionic Hamiltonian that you are generating directly. N is the number of operators, so plus minus, and plus and minus are the creation and annihilation operators. We apply a qubit converter that is going to take care of mapping your fermionic Hamiltonian into a spin Hamiltonian. And for this particular qubit converter, we're going to use a mapper that is a Jordan-Wigner mapper. And you see that when you are giving the second quantized operator that we described before, straight to your qubit converter, and you ask this to convert, this is going to return to you a qubit operator that's going to be based on Pauli strings. All the coefficients that you see in the fermionic Hamiltonian and the qubit Hamiltonian are based on the calculation of the one and the two body integrals. You can also go and use a parity mapper, where parity mapper has an intrinsic property of two qubit reduction. And you see that you can map also the Hamiltonian down to 2 qubits by exploiting symmetries in the qubit operators. This is the way that one can go down to the qubit operators. But if you would like to solve the problem and calculate the energy of the ground state, what would you do is that you would start again by defining the molecule that you are interested. Again, here we are using the hydrogen molecule. You would use the PySCF classical driver. You would have the qubit converter that has a Jordan-Wigner mapper, and then define a minimum eigensolver. You see here we're using a NumPy minimum eigensolver, which is an exact eigensolver. And what we do is that we're also defining a VQE unitary coupled cluster ansatz variational quantum eigensolver with trial wave function using the unitary coupled cluster ansatz. We are using the R simulator for the case of the unitary coupled cluster for the circuit simulation, whereas for the other case, we're using an exact eigensolver. Then, when you're doing this, you need to define either a unitary coupled cluster ansatz via a factory, or you can just define an arbitrary ansatz where you're using a single qubit and 2 qubit gates. Then, the calculation can be done in a way that you're defining a ground state eigensolver, you're providing a qubit converter in order for the ground state eigensolver to know how to map and how to convert the problem to a qubit problem, and you're providing a solver, which is a minimum eigensolver, the VQE solver. Then you ask for this calculation for the ground state eigensolver to solve the problem that defines the molecule that you are interested in and return to you the result that you see here. Here we are measuring the electronic ground state energy in hartrees, and gives also the information about the problem like nuclear repulsion energy and the total ground state. Then we are also measuring the particles, so the number of particles that you have in your system. For the case of hydrogen, it's 2, and the dipole moment. You can do the same using also the NumPy eigensolver, which is an exact eigensolver for the system. Then, if you would like to use the quantum equation of motion approach in order to calculate the energies of the ground states, the energies of the excited states, then you start again in the same way by providing an electronic structure problem and a qubit converter. And right now, the difference is that instead of using a ground state eigensolver, you're going to use a quantum equation of motion. Quantum equation of motion, as you remember from the plot that I showed before, from the sketch of the algorithm, would require a method to solve from the ground state solution. And here you need to define a ground state eigensolver, and all the things that come on top of the ground state eigensolver are handled automatically by the quantum equation of motion algorithm. And you see now that beyond the ground state energy in the result, we are now having the results related to excited state energies. Okay, so with this in mind, you can think that all these things can happen automatically, and there's a high level of modularity and extensibility in our software that will allow you to make all these calculations and start developing new and more elaborate schemes and algorithms. Eventually, we also have a potential energy surface sampler, which we call Born-Oppenheimer Potential Energy Surface Sampler, BOPES sampler for short. And what we do is that we are providing some degrees of freedom, for example here the stretch, in order to calculate potential energy surfaces like the one that you see here. We are also allowing for bootstrapping and for extrapolation of the different techniques in order to make the calculation a bit more efficient. Okay, so let me go back to the presentation. So showing you the software, now it should be clear that all these algorithmic developments can be leveraged via Qiskit Nature and Qiskit Terra automatically, and one can think of how can experiment and start working in more and more interesting approaches to the system. It is important to know that using all the algorithmic components that I mentioned, one can now use and leverage the fact that the Qiskit Runtime is available. Qiskit Runtime allows you to do multiple executions for the different system in significantly reduced amount of time. You can submit a bunch of jobs that can be executed without the need to queue for each of the job independently. And this allows you to make a significant speed up in the quantum processor calculations. An example is the case of the lithium hydride with error mitigation that would require in the order of 4.8 billion quantum circuits. And by using the Qiskit Runtime and use all the APIs related to the Qiskit program, one was able to achieve a speed up in the order of 120 times, which is a significant speed up for this particular calculation. It is important to know that runtime is there and can be used in order to simulate and test new and more elaborate algorithms. You should keep in mind that there are also other chemistry-related applications that go beyond the electronic structure. We discussed up to now a lot about quantum chemistry and a lot about quantum computers and how can be used to simulate molecular systems and measure observables, energies, and define these kind of systems. But what we didn't discuss is that what happens if we go beyond the electronic structure problem. Beyond the electronic structure problem, there are multiple problems that one can think about. The first problem that I want to discuss a little bit about and give you some flavor without going into big details is the protein folding problem. For the case of the protein folding problem, there is the so-called Levithal's paradox. The Levithal's paradox is a think experiment that Levithal designed, where he said that if a protein were to attain its correctly folded configuration by sequentially sampling all the possible conformations, it would require a time longer than the age of the universe to arrive at its correct native conformation. But in our body, this is not happening. Proteins fold in significantly less time and are able to really capture their final folded form within micro to millisecond times. How is this happening? And this is exactly the paradox. So Levinthal's paradox is exactly the fact that we can do something in such a small time in our body that means that there are some dynamics that we just don't understand. And this gives rise to the question, what if we were able to sample all possible configurations and evaluate them in a single experiment? This is exactly what we wanted to do in a hybrid quantum algorithm that we devised. We started by defining the model of protein folding as a coarse-grained model where we're using a tetrahedrals of diamond-shaped lattice, where each bit can occupy one position in this lattice. Then what we did is that we encoded all the configurations and all the interactions between the different bits in this particular lattice in a Hamiltonian that is a classical Hamiltonian with some penalty terms. We made sure that this Hamiltonian system that needs to be measured, we are using a different aggregation function, which we call conditional value at risk, variational quantum eigensolver. And here, what we do is that we are sampling only the part of the distribution that is relevant to our problem. We are reducing the number of slots that we are accounting for in the aggregation function in order to make it more efficient and also help us develop better solutions in a faster time. The classical algorithm that we used for this particular case was a differential evolution algorithm like the one that you see on the left. And we started by devising an ansatz that is arbitrary to the Hamiltonian and has single and two qubit operations parameterized by a set of parameters theta. With this, we are constructing a state and we take only the relevant part using the conditional value at risk and then iterate with a classical feedback loop in order to get to the folded structure. All the configurations are encoded in the different bit strings, and we know that the one that has the minimum energy will correspond to the folded structure of the protein. You see that for the case of the angiotensin one, 22 qubits, and we were able to simulate and file into the fold. The same also with a 9-qubit neuropeptide, where we used the circuit that you see on the left, and we were able to capture the solution of the problem quite nicely. This was only to tell you that there are problems beyond the electronic structures that one can think about and can use hybrid quantum classical schemes. All the work that I mentioned about the protein folding is also available as a different problem in the Qiskit nature, and one can use it directly. Other applications that we have about near-term quantum computers is the one that you see on this slide. Here it's a summary of different applications that we have on the natural sciences, and I'm just going to give you one or two sentences of each of these. All of them are already published, so one can find them in the literature and get more information about them. On the top left, we have quantum machine learning for high energy physics, where we use a famous TTH analysis for the production of the Higgs particle, and we use quantum machine learning enhanced with some physical knowledge in order to make this calculation. We were able to identify the production of the Higgs particle in a dataset that comes from CERN, so from high energy physics, and we were able to calculate this. Then we have the molecular dynamic calculations. We were able to use some classical dynamics in order to get information about the movement of the hydrogen molecule. We were able to capture the thermodynamic observables using different molecular systems, and also do material design where we combine different structures and find the one that fits best in the environment. Eventually, we will also tackle the Fermi-Hubbard model and the transition of the Fermi-Hubbard model in the ground state using hybrid quantum classical schemes. You see that quantum chemistry is very important. It's one of the applications that are the most important in the natural sciences domain, but it's not the only one. And there are many things that one needs to consider which goes beyond the electronic structure problem. Okay, so the take-home messages of this lecture. Hopefully, I was able to tell you that quantum chemistry is important and there are many challenges to overcome to simulate efficiently quantum computers. There are a lot of things that one can consider and start thinking of how can we scale up these calculations, how can we do the next step, how can we start thinking about more and more interesting problems and applications. And quantum chemistry in the near-term quantum computers relies on hybrid quantum classical algorithms and can really tell us that the full quantum chemistry simulations are going to be hybrid in the near term, and as we go and as we move with the progress of the quantum computers, we will be able to start thinking about different algorithms and start developing more and more elaborate schemes. Then, the methods and the solutions, and the methods in order to make the solutions better already exist. We actually have already built the foundations in order to start developing more and more elaborate error mitigation schemes, and we're going to be able to perform better in the near future. Qiskit nature can be used to simulate chemical systems, and not only chemical systems, and gives a tool that is fully automated and can provide information about all the different algorithmic and application related components that one need to simulate chemical and molecular systems. Eventually, what I mentioned is that there are interesting problems that go beyond electronic structure and give much more information and much different applications that one can think about.